Okay, so in this concluding video on the motion of rigid bodies in 3D, we're going to take a look at two applications. We're going to take a look at the gyro compass, and we're also going to go ahead and take a look at the rotational stability of a wheel. So the first application we'll look at is a gyro compass. Now this is a device that is used in aircraft as an instrument to provide compass directions for navigation. All aircraft have a magnetic compass, of course, as a backup, but they can be kind of sketchy. Um, more reliable is to have a very fast spinning gyroscope. So that's what I've noted here in red. That's seated inside a gimbal arrangement. Now, what the gimbal allows for is the gyroscope basically is just free to keep its spin axis horizontal, which is how it's set to begin with, but it's otherwise free to turn. So net result of this is that there's no torque due to gravity here. The gimbal counters that out. So if we go and look at some typical location on the surface of the Earth, let's pick, I don't know, mid-latitude northern hemisphere. There's the Earth's rotation axis, like so. And usually you align your gyro compass to be horizontal with respect to your horizon. So we'll say that the axis perpendicular is the J prime axis. All right, so now if we look down from above, we'll just assume for the moment, we'll treat this more generically. A pilot would align it to north, but you don't have to. So if we look down on our compass from above, our gyroscope from above, like so, we'll go ahead and say that the rotational axis points in the K prime direction, and then to complete the coordinate trio, that would be the I prime direction. We'll say that the angle that the K axis makes with respect to, I'm sorry, I forgot to put in my compass rose here, north, south, east, west. The angle that the I axis makes with respect to north will be phi, and that the K axis makes with respect to north will be chi. That's not an X, that's a chi. And I also forgot to label in the our plane here is, so our I axis here is also going to be tilted an angle lambda, which is equal to your latitude. All right, so with all of that, we can express omega e in our primed coordinate system. So omega e will be equal to I prime omega e cos lambda cos phi plus j prime omega e sine lambda plus k prime omega e cosine lambda sine phi. All right. And the angular and our omega prime here will be equal to omega of the Earth plus the angular velocity of our primed system, the gyroscope here, which will be j prime phi dot. All right. Or I'm sorry, yeah. And the gyro compass will be churning at psi dot times k hat. So we can express our omega, which is the rate at which the gyro compass is rotating, as the omega prime plus the rotation of the gyro compass in there. My bad, this was a correction for the rotation of the Earth here. All right. And this is for the rotation of, say, the airplane or whatever. All right, so with that, we can go ahead and put that all together and express our omega. So it'll be I prime omega E, omega Earth, cos lambda, cos phi, plus j prime. We'll get a phi dot plus omega E sine lambda, plus a k prime, psi dot plus omega E cos lambda sine phi. All right. So we can go ahead and get the angular momentum. So it'll be equal to I dot omega. So in analogy to what we've done before, we're going to get that is equal to I prime times I omega E, because again we're picking our rotational axis to be our principal axes. So again, I omega E cos lambda cos phi plus j prime I times that stuff in parentheses plus k prime is times that stuff in parentheses from here. There we go. And again, we will make the identification that this stuff in parentheses is the spin s. So we can rewrite one more time. I prime I omega E cos lambda cos phi. Oops. Plus j prime I times phi dot plus omega E sine lambda plus k prime is s. All right. Now, if we're going to keep our system horizontal, so looking here, any torque that is going to be exerted has to be exerted about the I prime axis. So we can write that the torque is equal to its magnitude times I prime. Okay, so following that, we can go ahead and do Newton's second law applied to rotations in the rotational frame. So ddt of r plus, we need to throw in omega prime cross L. Oops, just L. There we go. Now we can break this apart by components. So we'll take a look at the x prime component first. It's going to give me n is equal to I times ddt of omega E cos lambda cos phi, plus we'll take the x prime component of omega cross L. The y prime component, well, the torque in that direction is 0. So it'll be I times ddt of, we'll have a phi dot plus omega E sine lambda, plus we'll have to pick out the y prime component of omega cross L. And then finally, the z prime component. That'll still be 0. We'll have an is ds dt plus omega prime cross L, and we're taking the z component of that. All right. So probably behoove us to actually calculate the omega prime cross L. So we'll do that. Omega prime cross L will equal, okay, we'll have an I prime, omega E cos lambda cos phi I omega E cos lambda cos phi j prime phi dot plus omega E sine lambda and I phi dot plus omega E sine lambda. And then for our k prime component, omega E cos lambda sine phi. Well, it's a terrible omega. There we go, much better. And is s. And we finish taking our determinant. All right. So when you do that, it turns out that when you do the k prime part, you're going to get a cancellation here. This minus that is 0 for what we can get out of it. So this will give, so we're left with I prime times a bunch of stuff. Yeah, same quantity in the parentheses there. Then we pick up an omega E cos lambda sine phi plus j prime. And this will be I omega E squared cos squared lambda sine phi cos phi minus is s omega E cos lambda cos phi. And then the last term is just 0. So there is no k prime term. So that immediately allows us to conclude that omega prime cross L sub z prime is equal to 0. So going back to what we had here, if this term is 0, is is a constant, so that means ds dt is 0, and that therefore implies that the spin is a constant. Yay! Now, for any kind of practical application, and also to try to make this much more computable, usually you spin the gyros up to be spinning at like the hundreds or usually thousands of RPM. So that means that the spin is going to be much greater than the Earth's rotation rate. So when we look at the y component of the torque equation here, so we'll look at that. Ny prime equals 0 will imply. All right, so we'll have 0 is equal to I ddt of phi dot plus omega E sine lambda plus I omega E squared cos squared lambda sine phi cos phi minus is s omega E cos lambda cos phi. Now here's the deal, is at least this term right here with the omega E squared, since it's omega E is so much smaller than s to begin with, an omega E squared term is going to be virtually 0. So we're just going to wish it away. Now, it'll be convenient for us to recall that chi is the complement of phi. So that means that minus chi double dot is equal to phi double dot, and cosine phi is equal to sine chi. So with those substitutions, we can plug into here and we get that I times chi double dot plus ISS omega e cos lambda sine chi is equal to 0. And again, here we're wishing away an omega e sine lambda there because, again, it's really small compared to a term with an s in it. All right. So we can divide through by I, and we can get into a standard form, chi double dot plus ISS omega e cos lambda over I times the sine of chi equals 0. Where have you seen this before? Think about it. I'll get right back with you. Okay, this is the equation for a pendulum, right? No, I'm not going to make us go into elliptic integrals or anything like that. But the moral of the story here is that the gyro compass will oscillate like a pendulum around north. So if we had it initially aligned to north and we bop it over some angle chi, it'll oscillate back and forth around north. Now, in the real world, these things are set up to damp a little bit. You intentionally give a little bit of drag to the gimbal, and so it'll eventually settle in to 0.2 north. So no matter how we go ahead and turn our plane, thus changing our phi dot, having a phi dot momentarily. So we turn our plane when we do that. The gyro compass will try to drag along with the plane, but then it'll oscillate back and forth around north and eventually settle in. All right, so that's one example. The other example I wanted to look at is the rotational stability of a wheel. This has great application for kids when they're learning to bike. I don't know about you, but it was the toughest thing ever for me to figure out how to keep a bike from falling over. Of course, there's much better techniques now. Usually we give kids, nowadays the recommendation is to give kids gliders that don't have pedals so that they can just work on keeping the glider, the two-wheeled glider stable. And you let them play with that for 6 months or whatever, depending how quick a study they are. And then you can swap in a bike, and then they can learn how to do the pedals on top of that. For me, when I was a kid, I had to do it all at once, learn both how to pedal it and keep it stable. And it took me forever to figure out that I had to pedal as fast as I possibly could to keep the bike from falling over. Now, the puzzle that you might have is, why is it now that as a grown-up you can actually pedal kind of slow and the bike doesn't fall over? That's what we're going to go ahead and take a look at. So I'm just copying badly the drawing in your text here. So this is our point of contact P. Center of mass is O. Gravity will be acting down right there. And we're going to have some sort of reaction force from the ground, which your book calls FP. All right. So while we're churning, that's going to be your phi. All right. And let's go and put in our coordinates following the book. That's going to be J prime, and then tilted over. An angle theta here is going to be your K prime there. All right. So with all that, I can start with Newton's second law. Fp plus mg, plus mg equals m dv cm dt. All right. All right, so if we take our position vector from O to P and cross that into our FP, that will give us our torque. So that's dl dt there, right? So solving that for FP, we get ROP crossed into m dv cm dt minus mg has to equal dl dt. All right. So if we think about it, though, VCM is going to be omega crossed with RPO, which is equal to minus omega crossed with ROB. All right. So we can go ahead and substitute that in for VCM there. So now we'll have minus ROP crossed into m ddt of omega cross ROP plus mg, because of blowing out the minus sign, equals dl dt. All right. But taking a look at here, if the radius of the wheel is a, ROP is minus j prime times a. And we can write g as minus g times j prime sine theta plus k prime cos theta, just projecting down. Okay. So we'll substitute all that in. So now we have minus a j prime crossed into m ddt of omega cross a j prime plus mg without a vector over it, j prime sine theta plus k prime cos theta. And all that has to equal dl dt. All right. Now, unfortunately, that dl dt is being evaluated in the space frame, and we need to do this in the rotating frame, so we're going to have to do that whole ddt goes to ddt in the rotating frame plus omega prime cross whatever. So that's what we're going to do. So pulling out factors where we get them, we have minus ma squared j prime crossed into d omega dt evaluated in the rotating frame plus omega prime cross omega cross j prime minus MGA J prime cross J prime sine theta plus K prime cos theta. That equals dl dt, evaluating the rotating frame, plus omega prime cross L. Okay, thank God for small favors. That's going to be 0. You take it where you get it. So, plugging in from what we've found from before, remember that we've found that omega prime is equal to I prime theta dot plus J prime phi dot sine theta plus K prime phi dot cos theta. Omega without the prime was I prime theta dot plus J prime phi dot sine theta plus K prime S. And L was equal to I prime I theta dot plus J prime I phi dot sine theta plus K prime IS phi dot cos theta plus psi dot. Oh, no, sorry, that's just S. ISS. Awesome. So we'll do the same thing. We'll let chi equal 90 degrees minus theta. So then omega prime becomes minus I prime chi dot plus J prime phi dot cos chi plus K hat prime phi dot sine chi. Omega will be minus I prime chi dot plus J prime phi dot cos chi plus K prime S. And finally, L will be minus I prime I chi dot plus J prime I phi dot cos chi plus K prime IS S. All right, now in normal writing, we would hope that our phi dot, our theta, is about 90 degrees. And that means that chi would be about 0, which means that sine chi would be approximately chi, and cosine chi would be approximately 1. Also, while we're at it, we're going to assume that we're not churning the bike too terribly fast, so then we can let phi turn the handlebars too fast. So we let phi be approximately 0, which means that the sine of phi would be approximately phi, and the cosine of phi would be approximately 1. All right, so putting into everything that we got up there, that now gives us omega prime is minus I prime chi dot plus J prime phi dot plus K prime phi dot chi, which will be approximately 0 because chi is approximately 0. So by the same token, omega will be minus I chi dot plus J phi dot plus K S. And then finally, L will be minus I prime I chi dot plus j prime I phi dot plus k prime is s. Whoa. All right. So with all of that, where we had last left our stability criterion, we'll call this guy here dagger. Our dagger now becomes minus ma squared j prime crossed into minus I prime chi double dot plus j prime phi double dot plus k prime s dot crossed into j. Still inside the square brackets, plus a minus I prime chi dot plus j prime phi dot crossed into minus I prime chi dot plus j prime phi dot plus k prime s crossed into j. Okay, that gets us out of those square brackets minus mga j prime cross j prime plus k prime chi. Like I say here, at least we get a j cross j is nada. So, right. So that left-hand side there, go ahead and so then the right-hand side, so that's just the left-hand side, my bad. The right-hand side, which is the dl dt plus omega cross L stuff, that'll be equals minus I prime I chi double dot plus j prime I phi double dot plus k prime is s dot plus a minus I prime chi dot plus j prime phi dot crossed into, I think I need a little more room there, so crossed into minus I prime I chi dot plus j prime I phi dot plus k prime is s. Yeah. All right. Now here I'm going to say when you evaluate the cross products, you're also going to wind up getting a lot of terms of order chi square and phi square, and you can drop those because we're already assuming that chi and phi are nearly zero, so if we square them, that makes it even smaller. So dropping terms of order chi squared, that's about the worst O I've drawn in a long time. Order chi squared and order phi squared. All right, and we'll equate components and get. So for x, we have ma squared chi double dot minus s phi dot minus mga chi equals minus I chi double dot plus is s phi dot. The y component is just going to give me 0 equals I phi double dot plus is s chi dot. And the z term will give me 0 equals s dot times is plus ma squared. All right, well, immediately the z relation here is going to give me that S dot equals 0, because both these terms are just positive constants. And therefore, the spin is a constant, like we've seen before with these kind of things. Now, if we go and take a look a little more at the y equation, for our initial conditions, we'll assume that chi equals phi dot equals 0. That seems reasonable. You know, the bike wasn't falling over yet. So that will yield I phi dot plus IS S chi equals 0, or phi dot equals ISS chi over I. All right, we can plug that into the x equation. So we'll have ma squared times chi double dot minus ISS chi over I minus mga chi equals minus I chi double dot plus IS squared S squared chi over I. All right. I guess we can group the chi. We'll just try to get this into some kind of standard form, okay? And we can. So again, ma squared plus I chi double dot minus ISS squared over I plus IS squared S squared over I. Plus mga times chi equals 0. All right, if we multiply through by I, just to make it look a little better, I guess, we're going to get I times I plus ma squared chi double dot minus, plus, plus, we're kind of rearranging this into standard form, is plus ma squared s squared minus I mga chi equals 0. Once again, we've got a simple harmonic oscillator. Woot! We aren't concerned about the period, we're concerned about the stability. It'll be stable if this is positive. So, to have stability, what this tells us is that s squared has to be greater than I mga over is plus ma. Oops. It's ma squared. All right, so if we think about a typical wheel, so neglecting the spokes and the hub, because the hub, although it weighs a lot, is right next to the axis. The spokes, yeah, okay, they don't weigh a bunch, and there's a lot of them, and they're kind of long, but the bulk of the weight is out on the rim and the tire, so we're just going to roll with that. You get that is would be ma squared, and I, the moment about a diameter, would be 1/2 ma squared. So if we put into our stability criterion, we get that s squared has to be greater than, 1/2 ma squared times mga over I. Our is ma squared times ma squared plus ma squared. So cancel, 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 cancel. We can lose 1 power of, so we can lose 2 powers of A there. We can lose 1 power of A here. So I got 2 in the denominator. So my criterion is that s squared has to be greater than 1/4 g over a. So, in other words, if you're a kid, to have a bike that fits, the radius of the wheel is small. You gotta pedal fast. Not only that, but since you're a kid, you can't pedal as fast as an adult could anyway, so you're probably going to be pedaling right at the limit of your effort in order to keep the bike stable. Once you become an adult, the wheel gets bigger. You can pedal more slowly, plus since you're bigger, you won't have to go as far into your maximum effort range to keep the bike upright. So that is why it is easier to ride a bike as a grown-up than as a kid. Okay, and that concludes this series of lectures on the motion of rigid bodies in 3D. The next series is going to be on Lagrange's equations of motion.